Okay, hello everyone. We're going to get started now. Thank you everyone for joining today. My name is James Truckle. I'm an applications engineer with Plexim, and I'm excited today to be reviewing how you can use the small signal analysis tools found in Plex for controller design. Since the focus today is going to be on using the analysis tools, we may not comment on every single detail within our Plex circuits that we're going to be using. However, please feel free to ask questions along the way, and we will do our best to answer. You can ask questions at any time using the GoToWebinar control window, and then we'll answer them kind of during the webinar or at the end, or we may follow up with you individually after the webinar. Okay, great. So I'd just like to start with a quick intro for those who might be unfamiliar with our company. The electrical engineering software Plex that we develop is quite widely used and adopted in various industries and in academic institutions worldwide. It is a complete power conversion system simulation package. It yields very robust and fast simulation results. It's available in two different flavors. One, Plex block set, works directly in the MATLAB Simulink environment. It's a fully integrated power electronics system simulation package. Plex standalone offers an independent solution. Plex features a comprehensive component library, which covers not only the electrical aspects but also the magnetic, mechanical, and thermal aspects of power conversion systems and their associated controls. We are a Swiss company founded in 2002, and in the US we have offices in Cambridge, Massachusetts, and in Seattle, Washington. So let's quickly go over the development tools that I'll actually be showing in today's webinar. So I'll be using Plex standalone today to demonstrate the capabilities of the built-in analysis tools. Models will contain components from the electrical component library, which includes both passive and active electrical components like resistors and semiconductors. The magnetics, thermal, and mechanical modeling domains are also available in Plex. All versions of Plex include these domains, but will not be needing them today. With the help of the built-in analysis tools and the controls library, I will design and model my controller. Plex does offer other tools that further support the simulation, development, and testing of power electronics controllers. And this includes offerings like the Plex processor and the loop capability, the Plex coder for auto-generating C code, and our real-time simulator called the Plex RT box. There are other webinars and videos that cover different topics using these tools. You can also reach out to us individually if you want to learn more. Great. So as mentioned, modeling and analysis in the Simulink environment is also available by using the Plex block set. As a pre-disclosure, when the analysis tools are used with Plex block set, the procedure is slightly different than what you will be seeing today. The analysis tools blocks are found in the Plex extras library in block set. You place these blocks directly into the Simulink level model and double click to set up the analysis. This is different from the menu accessible configuration settings in standalone that you're going to be seeing today. Great, so today the application that we're going to be using to demonstrate the built-in analysis tools is an auxiliary-based power supply based on the flyback converter topology. So because I will be saving some time by using a few pre-built models, we'll take a moment here to review what's already been developed. As I open new models, I'll explain the changes that we've made. So hopefully it's easy for you to follow the flow. As an input to the converter here, we have a single phase rectifier. We're using a simplified high frequency transformer with 3 output windings, 5 volts and plus and minus 12 volts. The total output power is around 30 watts. This is a very low cost, simple implementation. It's a popular choice for power supply designs. The topology provides isolation between the primary and the secondary sides. and it also then gives the designer the ability to provide multiple outputs for different voltage levels and a choice of positive or negative voltage for the output. So during this webinar, we will add an inner peak current controller, which will regulate the peak MOSFET current, and then also a voltage controller to regulate the 5-volt winding. As I mentioned, I'm going to present these control analysis tools within the context of a design example. So specifically for the voltage control loop of the flyback converter. Using the attached PDF found in the handout section of the GoToWebinar control window, everyone does have the opportunity to go through a similar design exercise and familiarize themselves with these tools later. You can email me after if you need the models for that exercise, and I'll be happy to send you them. This webinar will use a design flow that works well within the Plex modeling environment using these tools. There are, of course, other approaches and methodologies that are possible. So as a starting point, we will determine the small signal transfer function of the current controlled converter in the form of generating a Bode plot. And this will then allow us to design a voltage controller and then subsequently calculate the loop gain response to ascertain if that system is now stable. So as a quick review here, let's go over the peak current controller block, which is actually found in the Plex library. So this is a modifiable controller. It's part of the controls category. I'll be opening it up in Plex in just a minute, and you can see where it's found. It's based on an SR latch or flip-flop storage circuit. So at the beginning of each switching cycle, a pulse is applied at the set input S of the flip-flop, which also turns the switch on. The switch signal remains on until the maximum duty cycle, as specified by the user in the controller's parameters, is reached, or the current sent signal exceeds the current reference signal. Slope control is also included in the peak current mode controller to avoid oscillations if the duty cycle is greater than 50%, and it does this by subtracting a ramp signal from the reference current input. So let's get to work now. We'll open up Plex, as I mentioned, standalone. And you should now see a model in front of you in the Plex schematic on the right-hand side of the screen. So here we do have a model of that flyback converter with no closed loop control at all. So the gate of our MOSFET is connected to a pulse generator block. And I'll first run an open loop simulation here so you can see the output voltage waveform. I'll do this by going simulation and start. And you can see here that the startup transients are really not very smooth, hence the need to add a voltage controller. So this is what we're going to be working on. So you can see on the left-hand side of your screen, there's the Plex library browser. So we're going to be using this to add components to our library, to our schematic, and to implement our control architecture. So first, we should replace the pulse generator block with the peak current controller that we've been talking about. So I can use the search function and search for the component, and then I drag it into my schematic. First, I'll just connect the switch signal to the MOSFET. And now I can right-click this component. As with all components in the library that are subsystems, you can look under the mask and you can see the implementation as we've modeled it, and you can then modify it as you would for your own application. So we can see here the behavior described in the previous slide. If I double-click the peak current controller, we can see the masked subsystem parameters. So the only default parameters here that I'm going to change are just the duty cycle, which we'll set to 50%. I'll check this box and this box, which will display the parameters on the schematic for us to see. There we go. So next, what we want to do is we want to create a current sense signal to feed into our iSense of the peak current controller. So I'm going to do that by simply placing a resistor component, which I'll grab from my passives electrical library. Place this into my schematic. I'll wire it up. I will change this to 0.5 ohms. We can display this. And now I also need a voltmeter component. Again, utilizing the search function. Don't need to show the name of this component. Wire it up. And now I can actually just show a quick auto routing feature. If I click the peak current controller and I hold the Alt button, Plex will actually auto route the signal that makes sense. So here we go. So we've auto routed now our iSense signal. And now for the reference current signal, IREF, I'm actually going to first use a constant block, which we'll see a question in a second here. So I'm going to use, I'm going to specify a set point value here of 0.273 amps. So this is going to limit my actual peak inductor current to 0.546 amps, and it's going to create an output voltage here of 5 volts. So I'll open my scope again so you can see it live. You know, we can save this trace if we want. We can save it as sim1. And I can run this simulation again. And now you can see, you know, the regulation on the 5-volt output. So I'd like to ask a question to the audience. You can use the chat window if you want to respond, and you'll get some brownie points. You know, you don't have to respond, but just to think about this. You know, what's impractical about the controller that I just implemented? Give everyone just a second. Okay, so what's impractical about the converter system is that, you know, typically in a system we're going to have an outer voltage loop that provides this reference current for the current controller in order to regulate the output. So no trick questions here. Just to design the voltage controller, now we're going to now use the small signal transfer function of the current controlled converter to do that. We can also we can now get into, you know, these impulse response and AC sweep tools to get this function in the form of a Bode plot. Okay, so to do that, I'm going to open up another model. Great. So I've pre-configured this model to perform this impulse response analysis. I will explain the changes that I've made. So first things first, we have changed the input rectifier and capacitor. We've changed it to a 300 volt DC source component. The dynamics of the input rectifier are much slower than those of the flyback converter and can therefore be ignored. Simple simplifications like this don't affect our controller design, and they make the small signal analysis easier to execute. To obtain a Bode plot of the open voltage loop, we've added 2 special components to the model. So you can see here, we've added what's called a small signal perturbation block. So this component is added to our current set point value. We also need to add a small signal response to the perturbation to measure the perturbation at the 5-volt output. So here's our small signal response block that we're using to measure the output. These components, as I mentioned, or I may not have mentioned, are found in the controls category and then found down here in the small signal analysis subcategory of the controls category. I've labeled these as IREF primed and vout respectively, and now we can open the configuration settings of the analysis by going to the simulation menu and going analysis tools. Again, if you are in Blockset, this procedure is slightly different. So there's a few settings to highlight here. We've got the impulse response analysis selected as our choice of analysis. We've labeled it simply as impulse response analysis. This is a configuration you add and remove analyses as you see fit for your model. The system here, we've specified a period length, and it's the least common multiple of all the periodic sources in the model. So which in our case is the switching signal, or 1/50 kilohertz. The frequency sweep range should be a vector of the lowest, that includes the lowest and the highest perturbation frequencies. And then on the perturbation and response section, we want to indicate the perturbation and response blocks that we have, that we want to use for this analysis in our model. We only have one of each, so it's very easy for us. In the options tab here, we can specify the number of automatically distributed frequencies. 21 is what's set for by default, and we'll actually just leave it as default. So I'm going to start this analysis, and then I'm going to explain a few more things. So that was very quick. We're done. That analysis was super fast, and that's because the impulse response analysis is actually the fastest method that we have of generating a Bode plot. When run, the impulse response analysis actually first runs a steady state analysis in order to find the stable operating point of the system. The steady state analysis is based on a Newton-Raphson iterative technique, and it may not converge when the system is run from startup because the system is underdamped and the state variables in Plex are going to be too far from the final operating point. So the simplest method of addressing this problem is to simulate the system for a specified number of initialization cycles before the steady state analysis is run. And if we go back to our configuration settings and we go to the steady state options, we can see here that we have the ability to specify this number of initialization cycles. This then causes the Jacobian matrix to be calculated from an operating point that is closer to the steady state operating point, which increases the likelihood of convergence in the underdamped system, and thus allowing the analysis to run to completion. Great, so that's our analysis. So we can go now back to this frequency response. We can see the frequency response here of our current controlled flyback converter. I'm now going to save this data. So I'll go File, Export as CSV. I've got previous data from my testing here, so I'll just overwrite it as flyback, replace it. Great. So now at this stage, we are ready to start talking about that current controller, or sorry, that voltage controller. So I'll just go back to some slides here. Great. So what we're going to be implementing today is what's called a Type 2 voltage controller. So it's quite similar to a PI controller, but with the caveat that we're adding a high frequency pole to mitigate the high frequency switching harmonics. So this is the controller that we're going to be implementing. The Bode plot and transfer function of the Type 2 controller are depicted here. So you can see that we have a high frequency pole, omega p. We have a low frequency 0. And these 0 and pole locations, as well as the attenuation at the crossover frequency AV, these three make up our design parameters. And these parameters are now going to be selected with the aid of the open loop converter Bode plot. So the unity gain bandwidth of our system should be about 500 hertz, or we're selecting it to be 500 hertz, and this is 5 times higher than the 100 hertz input voltage ripple. So this will ensure that the controller will adequately regulate the output despite any input disturbances that we see. So going into Plex, just quickly on that note, I can actually measure on the converter Bode plot here. If I go to 500 on my cursor 2 here, so we're 500 here. So you can see cursor here, frequency 500. So you can see here that the gain required from the controller's midband range is minus 11 dB or 11 dB. So switching back to the slide again. Great. So the pole and the 0 locations are now selected so that its midband frequency coincides with the crossover frequency. So we've selected 100 hertz and 2 kilohertz. So with these parameters now selected in our transfer function, Kp, tau, and t can be calculated using the given formula. So at this point, a designer could now calculate the numerator and the denominator coefficients of the transfer function for this type 2 controller. In my slide, these coefficients are labeled as A1, B1, and B2. And as a first step in Plex, in simulation, a designer could now implement this controller behavior using the transfer function component from the Plex library. So that's an option that I do encourage everyone to pursue in their own designs. However, in reality, we don't have such a thing as a transfer function control IC component that we can buy. So we're going to skip this step and directly add an inverting op-amp circuit, to implement this type 2 controller behavior. So all of the necessary formulas to calculate the resistances and the capacitances are included here. They're also included on that PDF. I'm not going to go through the calculations of these variables at the moment. So let's go back into Plex and I can show you this implementation. Great. So this model is now containing the previously designed op-amp circuit. I can open this op-amp by double-clicking, and you can see the schematic is replicated in the slide that I showed previously. As I mentioned, you're encouraged to review the calculation of these variables, these resistances and capacitances. Also set up in this model is an AC sweep analysis. So we'll use this now to obtain the frequency response of the controller with the goal here to verify that the Bode plot of the controller matches what we aimed for in our previous design steps. So let's open up those analysis tools again and take a look. So again, here now we have a system period that's set to 0, and there's no, this is a non-periodic system, it's a passive network. So now we've set a frequency sweep range and the number of points that match those in our previous analysis, and that's purposefully, as you'll see when I'm doing some analysis after this. This AC sweep analysis is based on a sinusoidal perturbation technique. So the system is simulated for each perturbation frequency, and then the output response is measured. So let's run the analysis, and we can take a look at the frequency response. Again, that was very quick for this kind of simple system. The plot looks good to me. It does quite closely match the design parameters that we specified with our pole and our zero locations. So now what I can do is I'm going to save this data again, and I will save, click this, export as CSV, and we'll save this as the type 2 data. Great, so now that we have the Bode plot of the controller, we can actually now add it to the Bode plot of the converter to yield the loop gain of the system. So let me just explain that quickly in a slide. So the loop gain here is a term that's equal to KSGS, and it's used to determine if the closed loop response of the system is stable. The closed loop transfer function of the cascaded control system is here, and it's now possible for us to predict the stability of the system by calculating the loop gain of the system and then measuring the gain and the phase margins. The loop gain is calculated by summing the magnitude and phase responses of the converter and controller at the same frequency points. So conveniently, we have saved our analyses, both collected data for the same number of points at the same frequency. So now several programs we can use now to calculate this loop gain. Python is what I'm going to use, MATLAB, MathWorks, Microsoft Excel. There's a number of ways you could do this. I'm again going to just demonstrate it using a Python script. So let me show you what that looks like. Great. So again, I'm not going to go line by line. You can see here that it's written in the Python language. The script first reads our CSV data, and then it calculates the loop gain. It then processes the calculation for displaying in a plot. So very simple script here. Again, if you'd like me to send you this, I'm happy to do so. There's nothing too special about it, but I am happy to send you this as well as some of the models if you're interested. So let's run it. I'll run it from my terminal window. I'm already in my folder, good. So I can just execute the script. Okay. Great, so now you can see here that we have now the predicted closed loop response. We've predicted the closed loop response based on our controller and our converter frequency responses. So now what we can do is we can confirm this and then do some further analysis in the Plex environment. So I'm going to leave this plot open. I'm going to go back to Plex. I can close this. I can close this. And I'm going to open up my loop gain sweep. Great. So again, we're looking at a model that we've been looking at. There's no drastic changes here. What I have added is I've now added our type 2 compensator into the loop here. So we can see the controller that we've designed is now in our feedback path. We have a set point here of 5 volts that we'd like to regulate to. And now what we're doing is we can now verify the loop gain of the actual closed loop system by using the loop gain analysis tools. So the resultant loop gain frequency response should be the same as from our previous configuration. So this loop gain component, again, is found in the same small signal analysis tools and it's used to inject a perturbation into the feedback loop itself. The response is then measured here at the output to determine the loop gain of the cascaded plant and controller. So let's go back to the analysis tools settings or configuration options. We've talked about all of these settings already. Again, this is going to be an AC sweep. We're using the perturbation and the response both from the via the loop gain meter component. So let's start this analysis. You can see this one takes a little bit more time to run, but quite quickly we will get a nice Bode plot here to measure the simulated loop gain. So now what we can do is we can again turn on these cursors that I briefly showed before, and we can make a couple of measurements. So the first measurement I'm going to make is actually at 500. So we already have our first cursor there. So at 500 hertz. The second cursor I'm going to place at minus 180 degrees. Great. So so you can see here from the Bode plot that the you can see here cursor 1 about minus 100 degrees and cursor 2 minus 180. So we can see here that the phase margin is about 80 degrees. This is the difference between that minus 180 degree and the loop gain phase at 100 degree at the unity gain frequency that we've designed to be 500 hertz. So the gain margin at minus 180 degrees, we can see is about 19 dB, 20 dB. So these gain and phase margins do indicate that the system will be stable. And actually, if I go and if I can get this to work, if I can put these next to each other, you can see here, if you look at the green predicted loop and then comparing that to our Plex generated Bode plot of the closed loop system, they're the same. So this is good. Great. So now what I can do is I can use one last model here to really validate and test the type 2 controller. So the only difference in this model is you can see I've added the input rectifier back to the model. I can show you under the mask. I just did a shortcut to look under the mask. Same thing as right-clicking the component and go and look under the mask. And you can see here it's just a simple rectifier circuit, no tricks. We have we're generating an error signal here that we're using as an input to the voltage controller by using this sum block. So it's subtracting the measured voltage from the reference source. And then looking at the flyback converter, we can see that now we're actually including a load step in the model. So a switch component will be closing, thus changing the load halfway through our simulation. So let's open up our voltages, our output voltage scope, and we'll run the simulation. I'm just going to do a shortcut, Command T or Control T. Great. So our transient simulation finished, and we can see that the voltage controller is quickly regulating the output voltage back to 5 volts when a step change in load is experienced. Our startup transient is very smooth, much improved to our open loop operation of the converter. So I'd like to mention a couple last things about these analysis tools. So let's go back to the analysis tools. So you can see here when I open these tools in a new schematic or in a new system where I haven't already set up these analysis tools, it's a blank slate. So I do have to use the plus button to add an analysis. And 2 additional analyses are available in Plex that were not covered today. So the first, or the, I guess the last in this list, the multi-tone analysis can also be used to generate Bode plots for systems that may not have, that don't have a periodic operating point. So this could be required, the required analysis if you have resonant topologies, for example. This would typically be the analysis that you would use. The steady state analysis here is another very handy tool that can quickly generate steady state waveforms without running a full set transient simulation that may take several minutes to hours. So encourage you to look at these tools yourselves. That does sort of conclude what I was trying to show today. We can draw a couple conclusions here. Great. So, this exercise did explore some of the more advanced control design and verification tools built into Plex in the form of these small signal analysis tools. The impulse response analysis, the AC sweep, and the multitone can all be used to obtain Bode plots of converters and their control loops. These frequency domain analysis capabilities of Plex are based on classical control theory. And when you combine this with time domain state space representation techniques of modern control theory, you're able to design, model, and simulate very robust control schemes. So other tutorials and application notes on our website explore using the Plex library for the design of specific advanced power electronics converters and their associated closed loop control systems. For more information on the Plex analysis tools and state space averaging with Plex block set or even Plex standalone, please see the Plex user manual. If you do need support running these analysis tools for your own models, you can send us your model at support@plexim.com and we'll be glad to help.